Now we want to look at the last section on vector spaces, which deals with the notion of a basis, the dimension of a vector space, and the orthogonal complement of a subspace. So let's first start looking at what a basis is. So we're going to say that if we have a finite dimensional vector space V and some list of vectors in V, they form a basis for V if and only if they satisfy two conditions. First of all, the list spans V. That is to say that every vector in capital V can be written as a linear combination of vectors in the list capital U. But equally important, the list of vectors has to be linearly independent. In other words, no vector in U can be written as a linear combination of the other vectors in U, or equivalently, every vector in V has a unique linear combination of the vectors in U. Okay? So a basis is a linearly independent set of vectors that spans the vector space it's in. Okay, now there's some common examples of bases. For example, we usually talk about the standard basis E1 and E2, where these are just the unit vectors along each of the coordinate axes. And of course, we can generalize that to Rn, okay? But an important thing to realize is that the basis is not unique. Okay, so we showed before that there was another linearly independent spanning set for R2, the vectors 1, 1, and 1, negative 1. Okay, so the basis for a vector space is generally not unique. Now we want to prove something that's really important. We want to prove that any basis set for the same vectors, finite dimensional vector space, has to have the same number of vectors. And what we're going to do is we're going to prove a lemma first that's going to help us prove this theorem. The lemma is going to say the following. If we have a list of m vectors and they're linearly dependent, and the first one's not equal to 0, then we can claim that there is some vector in this list, the second on up to the mth vector, such that that jth vector is in the span of the vectors before it. And the second thing we know is that if we remove that vector, the span of the remaining list is the same as the span of the original list. Okay, so what we're saying is that if we have a list of m vectors that are linearly independent, the first one's not 0, I can find some vector in that list that's not the first vector that lies in the span of the vectors before it, and if I remove it from the list, it doesn't affect the span. So let's prove that. Okay, so I'm going to start off, I'm going to let U be a list of linearly dependent vectors. And then I know that there is some non-trivial linear combination of those vectors in capital U that equals 0. In other words, not all the coefficients are 0. So I'm going to go ahead, I'm just going to let J be the index, and in fact the largest integer, such that the coefficient is not equal to 0. So this is the largest J such that Cj is not equal to 0. And then I can easily go back and I can write Uj as a linear combination of the ones before it. Since that J was the largest one, okay, I can solve for Uj. You should convince yourself that this statement's true. It follows from the one before that. And now if I take that Uj out of the list, the span doesn't change. Okay, and I can show that because if I look at any vector in the span of U, it's written as a linear combination of all the vectors, and Uj might be one of them, but Uj can be written as a linear combination of the other vectors, and therefore I can write that vector in the span as a linear combination of the remaining vectors with Uj taken out. And again, this is a good thing for you to show. Okay, now I want to prove the main theorem. I'm going to prove this by contradiction. So we're going to prove that there are that if we have two different lists and we claim they're both bases for V, they have to have the same number of vectors in that list. So we're going to assume that there are two such lists that are both bases, but they don't have the same number of vectors. And just for sake of concreteness, I'm going to suppose that M is less than N, okay? One's less than the other, so let's just let it be M. And what I'm going to do is I'm going to start tacking on. So notice what we've shown. We make this claim that the list for capital U is shorter than the list of W. And here's what I'm going to start to do. I'm going to start taking vectors from W and putting them at the front of the list of U and taking out vectors of U. And I'm going to show that's going to give me a contradiction. So here's what I'm going to do. I'm going to note that W1 is in the span of U because U is a basis for V. And so therefore, it turns out when I put W1 at the beginning, that list has to be linearly dependent. Okay. Now, by our lemma, you notice that W1 is not 0 because the basis vectors are linearly independent, and we can never have a 0 vector in a linearly independent set of vectors. And so this tells us that there is, and we have a linearly independent set, so by that lemma we just proved there is a uj in the span of the vectors preceding it. And so we can remove it, renumber the u's, and now we note that this new list has the same span. And the span of U, by the way, happens to be V. Okay? All right. Now we're going to keep doing this. I'm going to put W2 at the front of the list. Okay, now let's think about what's going on. Okay, W2 is not equal to 0. And this list is linearly dependent because W2 can be written as a linear combination of the vectors before it. So I can take out a vector after W2. Notice that it cannot be W1 because W1 would have to lie in the span of W2 and it doesn't. So it has to be one of the U's. So I can go ahead and take out one of those U vectors, renumber, and now I have this new list that's linearly independent and spans V. And I can keep doing this. I can keep putting W vectors in front of the list. And every time I'm going to have to take out one of the vectors in U because the claim is that one of the vectors in the list is linearly dependent on the vectors before that. But none of the W vectors can be linearly dependent on the ones before that because since they're from a basis set, they're automatically linearly independent. And so what's going to happen in the end is I'm going to get the following set of vectors after I do this the nth time. And notice the span never changes every time I add one of the W vectors. So I claim that this now spans V. But this leads to a contradiction because notice that Wn is not in there. So it says that Wn has to lie in the span of V, which means Wn can be written as a linear combination of W1 through Wm, which says that W1 through Wm and Wn are linearly dependent. And that can't be true because any set of vectors in a basis set have to be linearly independent. And that's how we get our contradiction. So this is a theorem that's worth going over and thinking about. Okay, so there are some nice little corollaries here. The first corollary has to do with spanning sets in finite dimensional vector spaces, and it says that no spanning set can be shorter than the basis set. Okay. And the reason why that's true is I can use that method I just did a second ago. If I had a spanning set that was shorter than the basis set, I'd be able to put those spanning vectors at the front. Okay, and I would end up getting a contradiction. Okay. And so this tells us that any spanning set can be pruned down. Okay, if I have a spanning set and it's not a basis, what does that mean? Well, by definition of basis set, it means that the vectors are linearly dependent. And so we had that theorem, right? That said if we have a linearly dependent collection of vectors, we can always take one out and the span is the same. So we can take out all the linearly dependent vectors stepwise and eventually get them down to be a linearly independent set. Then they'll be spanning and linearly independent, and they'll be a basis set. Okay, now for linearly independent sets, and that's actually a consequence of our previous lemma. It's not hard to show that. That's what I was just saying. Now, for linearly independent vectors in a finite dimensional vector space, this also tells us that no linearly independent set can be longer than a basis set. Okay? And the reason why is we can use that exact same method we did in the earlier proof to show that. If the linearly independent was longer than a basis set, we could start to tack on linearly independent vectors at the set of the basis set, and we get the same sort of contradiction. But what this tells us is that if we have a linearly independent set, we can always extend it to get a basis set. In other words, I start with my linearly independent set. If it does not span V, that means there's some vector that can't be written as a linear combination of those vectors. I can add it to the list. And now that new list is linearly independent. And if it doesn't span V, I can again find that vector that's not in the span and add it. And I can keep doing this, and eventually I have to stop because a finite dimensional vector space will be spanned by the basis set, and we know that that's some fixed number. Okay. And so again, we can prove this using the earlier lemma and that theorem we just proved. Okay. So spanning sets can always be reduced to a basis set. Linearly independent sets can always be extended up to a basis set. That's a very useful fact. Okay, we want to get to the notion of dimension. So since every single basis set has the same number of vectors, that allows us to define the dimension of V. For a finite dimensional vector space, the number of vectors in the basis set for V is called the dimension of V. Okay? This dimension definition is well defined because we just showed that all bases have to have the same number of vectors for a finite dimensional vector space. It's worthwhile just noting that subspaces of finite dimensional vector spaces are themselves finite dimensional vector spaces, so they also have dimensions associated with them. And in Rn, as an example, we know that one basis is the n standard basis vectors e1 through en, and therefore the dimension of Rn is equal to n, which we already know. The last thing I want to talk about is this thing that we call the orthogonal complement of a subspace. So we're going to say that we have some subspace U of a vector space V, and we're going to say that W is an orthogonal complement of U if W is a subspace, first of all, and every vector in W is orthogonal to every vector in U, and the intersection is the zero vector. So I should write up here also that W is a subspace. That's important, okay? Now, we can kind of think of a simple example of this. Suppose, for example, U is some plane in R3 that goes through the origin, and W is just some vector orthogonal to it. It's the normal to that plane. W is the orthogonal complement of U. Okay, their intersection is only the zero vector, and together they basically, and every vector in W is orthogonal to U and vice versa. Okay? All right, there's some important things about orthogonal complements. The first is that if we have an orthogonal complement of a subspace, then every vector in the vector space can be written as a linear combination of the basis vectors of those two subspaces, and that linear combination is unique. And I'm not going to prove that, but you can, okay? It is kind of obvious that u and w form a basis for v, because every vector is either orthogonal to all the vectors in u or it's not. Okay, so it's either in u or in w. Okay. So just as an example, if u is basically the two standard basis vectors e1 and e2 and w is e3, then we notice that every vector in R3 can be written as a linear combination of these three basis vectors, and that linear combination is unique. Okay. I won't ask you to prove theorem 3. Okay, it can be a little tricky, but you definitely have to know it. Okay, statement 4, though, you do want to be able to prove, which is that if u is a subspace of v and w is its orthogonal complement, then the basis vectors of u and w together do form a basis for v. And the reason for that is, first of all, the basis vectors of u and w span v. The reason why is every vector in v is either in u or in w. Why? Because every vector in v is either orthogonal to all the vectors in u or it's not. Okay? And it's easy to show that these basis vectors are linearly independent. Okay? Because no vector in w can be written as a linear combination of the vectors in u and vice versa. All right. You have to show these things, but at this point you have enough information that you can actually show this. And third, we go ahead and we use a definition of basis. Okay, so we have a spanning set that's linearly independent, therefore by definition of basis, they form a basis. Okay. The last result we want is a corollary, which says that if two subspaces are orthogonal complements, their dimension has to add up to the dimension of the space they're in. And this actually follows directly from theorem 4. I've shown that that the basis vectors in u and w are linearly independent, and they span, and they're a basis. Therefore, the number of vectors in u and the number of vectors in w have to add up to the number of vectors in their combined set, which is a dimension of v. Okay? Because these vectors altogether, they span v. So this is one that you should be able to prove. Okay, we're going to go on and talk about the specifics of solving linear systems, kind of the details, and we're pretty much done with the abstract notions of vector spaces that we need at this point.